Hello everyone, my name is Philip Cheka, and today I'm going to present to you a webinar about green methanol. Let's start with take a look on what is the methanol and what is the green methanol. If you look at the molecular structure of methanol and green methanol, you will find very easily that there is no difference in the molecule itself. So it's all about the technology, how we produce the methanol, what feedstock have we used, and what technology have we used to produce the methanol molecule. If we look on the production capacity of methanol worldwide, you'll see that in 2022, the production capacity was about 171 or almost 172 million metric tons. Of course, the actual production was a bit lower, so it was about 111 million metric tons in 2022. If we look on the methanol market, you'll see that in 2021, the market was worth of 37 billion US dollars. In 2030, the predictions are that the market will be valued at 72 billion US dollars. So you see the market is growing. Of course, you can find here some main exporters and main importers of methanol. And if you look down a bit, you'll see the feedstock, the actual product, which is methanol, the derivatives from methanol, products or end use, and sectors. Let's take a look at the feedstock. So for gray methanol, we need natural gas or coal. But for green methanol, we need carbon dioxide and green hydrogen. So if we need carbon dioxide for a methanol, this can be a really good way to decarbonize our industry. Now, let's take a look at derivatives. There's a list of different molecules and different chemicals that we can produce from methanol. Of course, we can also look at the products or end use, but I really like to look at sectors. In which sectors the methanol end up? So there's a construction, automotive, electronics, pharma industry, packaging, solvents, paints and coating. You see that methanol is being used in wide range of sectors. So I would say that methanol is actually a brick or a pillar of modern civilization. If you look how methanol is produced today, you'll find out that methanol is mainly produced from natural gas, water, and enhanced air with oxygen. So you'll basically preheat all these feedstock together, and then you'll do a partial oxidation to bring the heat, and then you'll do the steam methane reforming, which will generate a syngas, and then syngas can be used for methanol production. Of course, as you're going to be producing methanol, you'll be also producing water, so then you need to separate the methanol from water. However, if you want to look on the green methanol, the feedstock is slightly different. We need carbon dioxide, and carbon dioxide can be obtained from various technologies. It could be obtained from cement production or steel production, especially from the blast furnace, or it can be obtained from the direct air capture. Another source of CO2 could be natural gas turbine, oil-fired or coal-fired boilers. And then we have also the green technologies that also produce carbon dioxide, like biogas production, gasification of biomass or municipal waste, or even ethanol fermentation. All of these technologies are sources of CO2. If you look on the feedstock for the green methanol and the second feedstock we need, that's hydrogen. So I listed here several technologies, the electrolyzer technologies that can bring and create green hydrogen. That would be PEM, alkaline water electrolysis, AEM, or solid oxide electrolyzer. The first two technologies, PEM and alkaline water, are the most major technologies. And I decided to use alkaline water electrolysis in my simulation because it's the most common technology in Europe that is used for creating and producing green hydrogen. Let's look at the power plant. This is the first part of our model. we have a combined cycle gas turbine. The turbine, which is sucking the air inside, compressing it, and in combustion chamber, we're going to burn the natural gas, spin the turbine, and generate electricity. The flue gas coming out still have high potential heat, and therefore we can utilize this heat with waste heat recovery section, where we're going to generate steam, and the steam will be used in the steam turbine to generate another portion of electricity. As the flue gas is going through the waste heat recovery section, it ends up in a stack. In our case, it ends up in a direct cooling tower. Let me uncover these pictures and show you the simulation, which is right behind those pictures. So here you can see the natural gas turbine exhaust, and the flue gas, which is going through all these heat exchangers just to generate low pressure, intermediate pressure, and high pressure steam. Once we get our flue gas through all these heat exchangers, the flue gas will end up in the blower. The blower consumes about 5% of the energy that we generated by the natural gas turbine. And the blower is here just to bring the pressure, just to elevate the pressure a bit, so we can make it through the direct cooling tower and the absorber, amine absorber. Direct cooling tower contains just the water, so there's a water circulating in the direct cooling tower. The purpose of the direct cooling tower is to cool down the flue gas to temperature about 50 degrees Celsius. In our case, 54, could be 55. And just so you know, if you would have SOx or NOxes in your flue gas, instead of water, you could use a caustic solution to get rid of this SOx or NOxes. But in our case, we have no NOxes or no SOx, so therefore we can use just a pure water to bring down the temperature to about 55, 50 degrees Celsius. Our flue gas is cooled now, so let's move to a carbon capture. Here you can see a carbon capture unit. This is a Petronova that has been built in Texas. If you look in a detailed picture, you'll find that on the bottom, there's a flue gas duct that's feeding the flue gas on the bottom of the absorber. This huge column is the CO2 absorber. The column next to it on the right is regenerator. We have CO2 compressor, cogenerative plant that is generating the flue gas, and cooling tower. Notice that the column is not round, but it's squared. If we are working with a huge amount of flue gas, building a column out of concrete might be a better option from a capex perspective. You can use a plastic casting inside to prevent the leakage of the vapor. Using a squared column might be beneficial because as the column grow in the diameter, the influence of the corner is smaller and smaller with a bigger diameter. Therefore, the absorber is squared and the regenerator is round. Let's look at the reactions that we can find in the absorber and in the stripper. The reaction go from left to right in the absorber and from right to left in the stripper. You see that some of the reactions are fast and some of the reactions are slow. The first reaction, creating carbonic acid, is slow. But to enhance this reaction, we are using amines. CO2 reacting with amine, chemically bonding and creating carbamate, which in stripper will be regenerated. CO2 will be released and amine will be regenerated. Let's look on the simulation. First thing that needs to be noticed is that we're using amine sweetening SRK. This is a thermodynamic package that we're using for the simulation. Amine sweetening stands for the liquid thermodynamic package. So in the liquid, in the aqueous liquid, we're using electrolytic package, which is amine sweetening. SRK stands for sulfur Quank, which is the package that is used in the vapor. In our case, the amine that we use is monoethanol amine, MEA. And we're not using a pure MEA, we're using a 30% solution of MEA. So it's a 30 weight percent MEA. Let's look at the gas that we're feeding to the bottom of the absorber. We're feeding about 500,000 cubic meters per hour, which contains about 35 tons of CO2. You see the pressure is just a bit above the atmosphere to make it through the absorber. From top of the column, we are feeding about 580 cubic meters per hour of amine solution, which is cooled down to temperature about 49 degrees Celsius. The reaction and the absorption is exothermic. Therefore, as you can see, the temperature of the vent gas is slightly elevated. The pressure is almost atmospheric. To prevent the losses of the MEA, you can install a water wash section on top of the absorber. CO2 is absorbed and gets into the rich amine. Here you can see a loading of the rich amine. If I scroll a bit down, you'll see that the loading is defined as the mole of CO2 per mole of amine. The amine doesn't need to be one amine, but it could be a mixture of amines, like AMP and piperazine. This mixture might be, the AMP and piperazine might be a bit better for carbon capture purposes. And here you can see how the AMP and piperazine looks like. But in this case, we used MEA because it's the base and industry standard for carbon capture. Once we capture the CO2 and it gets into rich amine, we're using a pump here to pressurize it to about 5.5 bar. The reason why we want to pressurize our rich amine is to bring as much heat as possible from the lean amine. So we're trying to do as much recuperation and heat integration as possible, while we want to keep an eye on the amount of vapor that is formed in the lean rich heat exchanger. If we wouldn't pressurize it enough, some of the CO2 will break out from the liquid and can corrode the lean rich heat exchanger. Once we preheat the rich amine, we can depressurize it a bit and feed it to the stripper. The pressure here is the main key factor for the stripper. If you're going to use a lower pressure, you can expect higher consumption of steam. You can expect higher diameter or bigger diameter of the stripper because there is going to be lower pressure. So the vapor is going to take more volume. But at the same point, you can expect a lower temperature on the reboiler, which is beneficial if you are concerned about the degradation of the amine. If you have a higher temperature, the amine will degrade faster. If you have a lower temperature, the amine will degrade slower. If we use the higher pressure, you can expect stripper to have a smaller diameter, but the amine will be degrading faster. We captured about 34 tons of CO2 from the original 35.5 tons. The overall CO2 recovery is about 95%. Of course, we can increase this CO2 recovery by changing certain factors, but in this case, 95% is satisfying. And once again, it will very much depend on the specification you have. Usually, the specification is about the CO2 recovery that you want to achieve. Let's move to a compression part. Here we have a duplicator. A duplicator is a simple stripper that is multiplying by 200% the feed the feed stream. And then I'm dividing it 50-50. So I'm going to have this stream multiplied. First part will go to a direct conversion methanol synthesis, which is one option that we studied. We need a stages of compression to achieve 50 bar. And the second option is a reverse water gas shift reaction with methanol synthesis, where the initial pressure is just 16 bar. What I can recommend here for the packing of the absorber is to use a structured packing. And that's mainly because we want to have the lowest pressure drop as possible for the absorber, because we are already working with a very low pressure. We covered the carbon capture part. Let's move to the alkaline water electrolysis. Here on the picture, you can see one of the biggest electrolyzers that has been manufactured. I think the capacity of this electrolyzer is about 20 megawatts. The building unit cell, or the building units of every electrolyzer, is cell. You can put cells behind each other and create a stack of cells. Every cell is defined by area, which could be in square meters or square centimeters. And the most important thing connected with the area is the current density. That means how much current you can supply for a certain cross-section area. Another very important thing is cell voltage. We have a terminal to voltage and overpotential voltage. If you would have ideal electrolyzer, there would be no overpotential voltage. But we live in the real world where overpotential exists, and therefore we have terminal to voltage and overpotential voltage. The terminal to voltage is the minimum voltage required to drive the reaction. It's defined by the temperature and influenced by temperature and pressure. It's given thermodynamically, and it's stable and is not varying much. ProMax can calculate terminal to voltage from the Nernst equation. Overpotential voltage, on the other hand, something what ProMax cannot calculate. That's something what needs to be obtained from the original manufacturer of the electrolyzer. What is the overpotential voltage? So the cell requires more energy than is thermodynamically expected to drive the reaction. So the extra energy is lost as a heat. That's why we see a difference between the temperature on the inlet and the outlet of the electrolyzer. Overpotential voltage is influenced by the material of electrodes, and it varies across the operation conditions, which means that temperature and pressure has influence on the overpotential voltage. Temperature and pressure also have the influence on the terminal to voltage, but it's not as significant as with the overpotential voltage. The material of electrodes has also influence on the overpotential voltage, but it's something what manufacturers can influence. Some manufacturers are considering more precious metals for the electrodes, but there seems to be a downside because those materials like gold are extremely expensive, and it doesn't worth it to use much more expensive electrodes for smaller overpotential voltage. Polarization curve. Polarization curve is one of the most important curves or things that you can use and find for the electrolyzer. It's the most defining thing. What is the polarization curve? On the x-axis, you can see a current density. On the y-axis, you can see a cell voltage. If you notice, there is a terminal to voltage, which is the dashed line. It's about 1.47 or 1.48 volts. And as you can see, it's stable and it's not varying across the current density. So as we're going to be changing the current density, the terminal to voltage will be stable. But there are all the other losses, like protonic ohmic losses, activation losses, mass transportation losses, electrical ohmic losses. And all these losses, if we sum them up, we're going to get the overpotential. So the overpotential is the difference between the cell performance and thermal voltage. On this picture, you can see that all these arrows, which are showing you the overpotential voltage. Let's look at the electrolysis plant in 3D. This is a picture from Nel Hydrogen. You see there is a stack of electrolyzer, two vessels, one for separating the hydrogen from the KOH mixture or KOH solution, second for separating the oxygen from the KOH mixture or KOH solution. On top, there are two plate frame heat exchangers, and on the bottom, you would see a pump. Let's scroll down and see how this model looks like in ProMax. First of all, we're using an electrolytic package. It's electrolytic ELR with SRK. So once again, we're using for aqueous solution, we're using electrolytic package because we're using 30% KOH solution. For SRK, that's for the vapor package. If we look inside the electrolyzer block, you'll find out that we are using a certain water electrolysis technology, in our case, alkaline water electrolysis. You'll find here pressure drop to the oxygen and pressure drop to the hydrogen. These are input values, a temperature change between the inlet and outlet, total hydrogen mass yield, total hydrogen standard vapor volumetric yield, water conversion, current density, and so overpotential voltage. Here you can see that I checked the polarization curve. So my electrolyzer is actually using a polarization curve. Let's see how the polarization curve looks like. We have a current density data, and we have overpotential data. To describe the trend, we are using Lagrange line. So it doesn't matter how much power I'm going to supply to my electrolyzer, it will always understand what is the current density and how is it linked to the overpotential data. If you would use higher current density than what is the maximum, the ProMax will give you an error and warn you about it. We have a number of cells. We have number of cells per stack. We have number of stacks in parallel, and crossover of hydrogen and crossover of oxygen. Crossover of hydrogen or crossover of oxygen is something which you should also ask your manufacturer about. Notice that crossover can change throughout the lifetime of the electrolyzer as the membrane is going to be slowly degrading. One of the most important things you can find here is the electrical efficiency. It's in kilowatt hours per kilogram. If you look at the results, you'll find here that one cell is 1 square meter. In stack, we have 100 cells, so the stack is 100 square meters. And of course, we have 250 stacks in parallel, so you'll get the total area. Here is current and voltage. Now, notice that this is the voltage for one cell, and this is the power for one cell. Now, there is terminal to voltage and terminal to power, and overpotential voltage and overpotential power. So now you can see how much power has been used for the reaction to split the water into hydrogen and oxygen, and how much power is being lost as a heat. Let's look at the amount of power that has been calculated. 236 megawatts. If we look at the total power, you see this cell is blue. That's because solver has been applied here. If I double click on the solver, you'll see that we specified a certain equation. What this equation is doing is basically taking the flow of CO2 that we already captured, and it's trying to multiply it by 3 to calculate the stoichiometric amount of hydrogen that is necessary for methanol production. So the stoichiometric ratio should be 3 moles of hydrogen for 1 mole of CO2. With knowledge of the amount of CO2 that I'm producing, I can put a solver on the power of the electrolyzer to calculate the amount of hydrogen that will be produced. So what I'm basically doing here is, I don't know how much power should I supply to my electrolyzer, but I do know how much hydrogen I need for the methanol reaction. So the ProMax can calculate for me how much power is required. Let's look at a few more things on this flow sheet. The solution is 30% KOH, rest of it's water. Of course, there is a piece missing, which is mainly in this case oxygen, because we are looking at the anode section. The water with KOH and oxygen is fed to the separator where oxygen is separated. KOH solution is cooled down and circled back into the electrolyzer. On the other side, KOH hydrogen together with KOH solution is being produced, and we're gonna separate it in the first separator. As you can see, part of the KOH end up in the vapor. This is something what has been achieved with the entrainment. If I look in my separator and look at the bookmark called entrainment, you'll see here there's a numerator value and denominator value, which is basically telling me how much vapor or how much liquid end up in the vapor. This is a user specification. And what it's trying to do is to estimate a certain amount of vapor, a certain amount of liquid might end up in the vapor. That's what we call a carryover. So there might be a certain carryover of your KOH solution into the vapor. To get rid of the KOH or KOH solution from the vapor, there is several strategies. One of them could be using a column, feeding the fresh water from the top and scrub the KOH back into the system. The other way could be using an air cooler to knock out the water, and then on call ester, separate the mixture. Of course, due to the crossover of oxygen, part of the oxygen will end up on the hydrogen side. For that reason, we can use a deoxo unit. This is just a normal Gibbs minimization reactor that will convert hydrogen together with oxygen to water. Once we produced hydrogen, which is clean, and we get rid of all the contaminants, we can pressurize it and feed it to our both options for green methanol production. So far, we covered the carbon capture part. We prepared the carbon dioxide. We covered the electrolysis part. So we prepared the green hydrogen. And now we're going to mix them together and look on the direct conversion. That's the first technology that we're going to study. We have SRK polar, which is the environment or thermodynamic package that we are using. SRK polar has tuned binary coefficients between methanol and other molecules like water or hydrocarbons. So SRK polar is the best package for any kind of simulation that has methanol inside. Now, the hydrogen and CO2 are in stoichiometric ratio, 3 moles of hydrogen, 1 mole of CO2. We're going to mix them together, preheat them, and we're going to feed them to the direct conversion reactor, where first portion of methanol will be produced, carbon monoxide will be produced, and carbon dioxide and hydrogen will be consumed. The temperature is limited to 250 degrees Celsius. The reactions that we are using are listed here. This is the conversion reactor, so we are using fractional conversion for each of these reactions. The first reaction is producing methanol. Last reaction is producing carbon monoxide. The two reactions in between are side reactions producing methane and ether. The catalyst is copper zinc oxide doped with zirconium oxide. The conversion is about 21%. Let me show you how the reactor is specified. Here you can see a process data. So a type of the reaction or the reactor is conversion reactor. This is the reaction set. And then you see just the pressure drop, which in our case is 0 bar for simplicity. Of course, the reaction set is the most important thing. So here you see all the reactions. And you can also find them here, where if you look at the conversion, you'll find the same numbers as were displayed from the paper in the ProMax. This way, you can very easily specify your conversion reactor. Once we produce a first portion of methanol, it will be fed to the crude methanol separator, where methanol is being separated from the unreacted gases. The unreacted gases will be fed to the splitter. Part of them will be purged. About 25% will be mixed, will be recycled back for the first reactor. And about 75% will go back, will go to the second reactor, methanol synthesis reactor. Here, the majority of methanol is being produced. Let's look at the reactions in the second reactor. First two reactions are producing methanol. There is a mistake. This should be carbon monoxide as the reactant. And all the other reactions are side reactions, producing other molecules, other hydrocarbons. Their fractional conversion is very low, so you'll see a small number of these contaminants. Catalyst could be copper zinc oxide or zirconium copper zinc oxide or copper zinc oxide, but the zirconium helps with the conversion of carbon dioxide to methanol. And here the feed is quite different, or the recommended feed. It should be 1 mole of CO2, 1 mole of carbon monoxide, and 4 moles of hydrogen. Let's look at the graphs below. You see the carbon monoxide conversion is about 50%. Carbon dioxide conversion is about 27%. So carbon monoxide is much more reactive, and it's much easier at producing methanol. Important thing here would be also that there is, as you can see, above temperature of 250 degrees Celsius, we see a drop in the conversion rate. That's because the catalyst itself will become deactivated at higher temperatures. That's why we want to limit them to maximum temperature about 250 degrees Celsius. Once again, I can take a look inside the reactor. Look at the process data. Once again, it's type of conversion reactor. Here's the second set. And if we look at the reaction set, here will be specified all the reactions. So there are 9 reactions. And we can take a look at their conversion constants. In ProMax, you can not only specify a conversion reactor, but you can also specify the kinetic reactor. If you know the kinetic value, the kinetic equation, if you have those kinetic data, If you know the adsorption terms on the catalyst, you can specify it there too. Once the raw methanol is produced, it contains a lot of water and also unreacted gases. The raw methanol will be fed to a vessel where we drop down the pressure and portion of the unreacted gases will be taken away. And we are left with mixture which is approximately 50% methanol and 50% water. The first column, a topping column with 40 ideal stages, is here just to remove a portion of those unreacted gases. So the first column here is just to remove the gases. Second column is a refining column. Once we get rid of the unreacted gases, we can separate the methanol from water. This way, we can obtain a pure methanol. The methanol recovery system might be composed of 2 columns, but we can also make it more complex with a better heat recuperation with a 3-column system. So far, we covered the direct conversion. That's one of the options. Let's look at the other option, which would be reverse water gas shift reaction followed by methanol synthesis. Once again, we're using SRK polar. We are feeding the hydrogen together with CO2, but the portion of hydrogen, about 1/3, is taken away and fed later on. Hydrogen needs to be depressurized a bit because from the pressurized alkaline water electrolysis, we're going to get the hydrogen at 30 bar. So we need to depressurize it to about 16 bar so it can be used for the reverse water gas shift reactor. Notice that there is a slight difference between the temperature. That's because hydrogen has negative Joule-Thom's coefficient, and when we're going to depressurize it, it's going to heat up. Hydrogen, together with CO2, is preheated to about temperature 420 degrees Celsius, but to preheat it to the about 650 degrees Celsius, which is required by the reverse water gas shift reaction, we need an extra source of heat. In this case, it could be a natural gas with air, which could be burned in burner, and the heat could be used for preheating. The rest of the power or rest of the heat that we're going to generate from this reaction can be used for generating steam, high pressure steam and low pressure steam. CO2 generated by the burner can be captured in the carbon capture unit and also used for the hydrogen for the methanol production. From the reverse water gas shift reaction, you'll notice that the temperature dropped down significantly. That's because reverse water gas shift reaction is endothermic. If we look at the composition coming out of the reverse water gas shift reaction, you see that no methanol has been created. Reverse water gas shift reactor is basically producing syngas from CO2 and hydrogen. That's why we see carbon monoxide, water, CO2, and hydrogen. It's an equilibrium endothermic reaction. And here you can see how the reverse water gas shift reaction actually looks like. Hot syngas needs to be cooled down and pressurized so we can do the conversion of hydrogen, CO2, carbon monoxide to convert them to green methanol. As we're going to cool down our syngas, water will drop out. This is very nice because then if we're going to remove the water here, we don't need to remove it later on in the distillation columns, And it also is going to shift the equilibrium towards the methanol. Here you can see two compressors, one for hydrogen and one for the syngas. Flow rates of hydrogen that has not been used for the reverse water gas shift reaction, the flow rate of the syngas. And here we're going to have only one reactor. Reaction mixture needs to be once again preheated. And notice how much methanol is being created in this one step. So in this case, the first portion, the reverse water gas shift reactor, won't create any syngas, but it will create, won't create any methanol, but it will create a syngas that will be used in the methanol synthesis reactor. Now, this reactor contains the same catalyst, it has the same reaction set as the second reactor in our first case, in direct conversion. Once the methanol is produced, it's cooled down and separated in the flash separator. Unreacted gases are fed back with the compressions or recycled back and feed it to the methanol synthesis reactor. Produced methanol with water is once again fed to the system of two columns. This case is a little bit different because it contains much less water. So it's about 70% methanol and about 30% water. Once again, the topping column is here to remove the unreacted gases. And methanol is refined in the refining column. This way, we're going to obtain a pure methanol stream and almost pure water stream. Let's move now to conclusion. We captured about 33.8 tons of CO2. The CO2 recovery was about 95.3%. Standard vapor volumetric flow of CO2 is 18,357 cubic meters per hour. Hydrogen, on the other hand, so we produced about 4.7 tons of hydrogen. The renewable power that was required for this green hydrogen was about 236 megawatts. And the standard vapor volumetric fraction flow was 54,645 cubic meters per hour. So just to compare the mass flow and the standard vapor volumetric flow, you see that hydrogen will require much bigger pipes or pipes with much bigger diameter than CO2. If we look at the methanol, we produced about 23 tons of methanol per hour. So if we would be running this facility 365 days a year, we would produce about 200 tons of methanol per year. If we would build about 550 of these plants, all methanol that would be produced will be green. If you look at the mass flow of CO2 and mass flow of hydrogen, you see that the methanol is about a half. It's roughly about a half. That's because when CO2 and hydrogen is reacting and producing methanol, water is also produced. That's the missing amount of mass. If we compare these two options, I have to say that direct conversion has been built on a large scale and reverse water gases have not. Direct conversion has definitely a few advantages. There will be lower temperature and lower compression power. However, the water in raw methanol is about 50%, which eventually requires more energy for the methanol to be distilled. Of course, this can be changed with the different setup of the reactors and the separators. Let's take a look at what are the future of the green methanol. So far we covered a big scale. In my opinion, this is a big scale. So we are looking at a natural gas turbine, carbon capture unit, electrolysis, and methanol production and purification. There are also other options, which might be a mid-scale, where we're going to use biomass with or municipal waste for a gasification together with steam. And the gasification requires pure oxygen, which can be obtained from electrolysis. So I see a big synergy between electrolysis and gasification. This way, from municipal waste or biomass, we can produce a syngas that is going to have low hydrogen concentration, but the hydrogen can be added from the electrolysis. This way, we can create a suitable syngas for methanol production. On a small scale basis, we can use a biogas that can be separated with membrane separation or just water separation. And the CO2 and hydrogen from electrolysis can be once again mixed and used for production of methanol. Let me finish this webinar with one insightful quote. Stone Age didn't end because we ran out of stone.